This is a problem looking at a hypothesis test for two independent averages. It says each year, the US Environmental Protection Agency, the EPA, releases fuel economy data on cars manufactured in that year. Below are the summary statistics on fuel efficiency in miles per gallon, and I just wrote the same table down to the side here. From a random sample of cars with manual and automatic transmission manufactured in 2012. Do these data provide strong evidence of a difference between the average fuel efficiency of cars with manual and automatic transmissions in terms of their average city mileage? Assume the conditions for inference are satisfied. Okay, this is looking for a difference. And I'm asked for the hypotheses, test statistic, that's our t-score or our z-score. It asks for our p-value, tells us to use technology, okay, and our conclusion. So we're going through the 4 steps of a hypothesis test. We'll write down our hypotheses here, and then we will switch to just the overhead for a while so we can see things better. We are testing for a difference between automatic and manual. Your null hypothesis when you're comparing two averages is going to be that your averages are equal. And you could write that as average for the automatic is equal to the average for manual, or if you wanted, you could write that as average for automatic minus manual is equal to 0. For the alternative hypothesis, I'm testing for a difference. So I'm going to have a does not equal symbol because I'm testing if it's not equal, if it's different. An alternative hypothesis, if I'm writing it as the subtraction, is going to be not equal to 0. When it's not equal to 0, that's going to be a two-tailed test. I'm testing for both more and less at the same time here. And now that I have these hypotheses, I can move forward with coming up with my model. And I'm going to be looking at automatic minus manual. I could really choose either order. This is going to follow a t-distribution. And as a rough estimate, and this is where that technology is going to come into play because we want to get a more accurate degree of freedom. That's the one value that's going to be a little bit off when we do stuff by hand. I'm going to take the smaller of the 2 degrees of freedom. The first degree of freedom there would be 25. Second degree of freedom would be 25. So very roughly, we're going to be using a degree of freedom of 25. In actuality, it's probably a lot larger than this, but we're going to see how much this changes the values. The average will always be 0 for hypothesis tests when you're comparing two averages, because I'm testing here, the claim is that they look the same. Our standard deviation is going to be the standard deviation for the first group squared over the number of samples. This is equivalent to that s over the square root of n if you simplified this. So that's that same standard deviation we had before. And I've got 4.51 squared for the other group over 26. I'm going to type that standard deviation. You might call it a standard error because it's based off of sample data. So I'm being a little loose with the vocab there because it's kind of filling 2 roles. 3.58 squared over 26 and 4.51 squared over 26. When I do this, I get a standard deviation for my model of 1.129 or so. Third step, my p-value step. I want to look at the likelihood of my data. Now, my data here is saying take the average for auto minus the average for manual. and I'm testing for does not equal. My auto difference, 16.12 minus the manual, 19.85. I'm going to type that into a calculator and see what I get. But then I will have, this will give me my value. I still have the center and standard deviation. So I'm going to find my t-scores the same way that I found them previously by doing value minus center over standard deviation. I've got 16.12 minus 19.85. And this gives me sample data of negatives 3.73. So if I were to draw the picture, the center of my curve is 0. I'm roughly counting by about 1.129. And 3, negative 3 is going to be way, way down here. And I want that much or more in both directions because I'm doing a two-sided test. Does not equals. I'm going to calculate my t-score by taking my sample value minus the center divided by the standard deviation. My sample value here is negative 3.73. The center is 0. My standard deviation is 1.129. I'm going to be careful with parentheses. Now, if you're subtracting 0, you really could just ignore that 0 and do negative 3.73 over that denominator. I'm still going to type it in. I got negative 3.30 as my t-score there. This is a two-tailed test, so that other t-score would be 3.30. Now I'm going to go into GeoGebra, and I'm going to look up that t-score. So let me pull up GeoGebra here. Give me 1 second. Okay, I'm in geogebra.org/classic, and I'm going to go into probability. And I'm going to choose the option for student. I'm working with the student t-distribution. It's going to ask for the degree of freedom. This is where that rough guess is coming in, rough guess of 25. We'll see what the actual standard deviation is here in a second. And I want to shade out two-tailed. So I'm choosing this option that has my brackets going out. I use degree of freedom of 25. And I'm going to use my t-scores. I put my t-scores in here, and I'll spit the p-value out over there. Negative 3.30. And on the other side, positive 3.30. When I do this, it gives me a p-value of 0.0029. Pretty small. Now, looking at the problem, it does want 4 digits of accuracy, so we might find that our answer is just a tiny bit off if we use this estimate. But let's see how far off after we do the conclusion. If I compare this to a neutral alpha level of, say, 5%, this is less than 5%. So I would reject the null hypothesis, which means I have evidence, or we have evidence, of a difference in average miles per gallon for automatic compared to manual. Okay. I want to double check my answers using GeoGebra here. So besides just having this probability calculator where I can find the student distribution, I'm going to start at GeoGebra from the beginning again. I'm going into probability, but this time I'm going to choose the option for statistic. And I'm using t-scores, and I'm looking at the difference of means, and I have difference of means show up here for a test, and I have difference of means show up here for an estimate. Estimate will be for confidence interval, test is for hypothesis test. And that claimed value is 0. And notice that's a gray block. I can't even change that thing. I can highlight it, but I can't change it. Alternative hypothesis does not equals. Pooling, I'm saying no to pooling. Pooling assumes that your standard deviations look the same. I don't want to make that assumption here. 16.12, 3.58, and 26. That was my information for auto. For the manual, it was 19.85. A standard deviation of 4.51, and a sample size of 26. Now, when I do this, I get a t-score of -3.303. Notice my t-scores are exactly the same. My p-value, I had roughly 0.002. And using GeoGebra, we got 0.002. So up to 3 decimals, we have the same level of accuracy, even though if you look at the degree of freedom, the degree of freedom is wildly different using technology. So my results for the p-value and the t-score, the things that matter, the t-scores will perfectly match up and the p-values will be super, super close, especially as your sample size gets larger. Degree of freedom, 47.55 is the actual degree of freedom. And the p-value using technology for the whole thing is 0.0018. I would do the whole thing by hand, just get a feel for it, and then I would double check your answers using technology. Let's fill things in. I'm testing for a difference. My test statistic is -3.30. I'm actually going to try just to see if it takes it, or one with the rough estimate. It might not, that's okay. And with this, I would reject the null hypothesis. So that tells me that there is evidence, it does provide sufficient evidence that there's a difference between the average fuel efficiency of manual and automatic cars in terms of their average city mileage. Full points. So even using that rough estimate, I still got a p-value that looks just fine here inside of MyOpenMath. So if you're worried about these things looking drastically different, I would try going through it by hand just to get a feel for this process, and then check with technology to see how close those things are. In practice, they'll be pretty dang close, assuming you have reasonable sample sizes. I hope that shows how to do this in kind of 2 different ways, and also for you to double check your work. As always, I am around if you have questions.